Guys, welcome back to TechDose, and in this video we will look at valid arrangements of pair problem, which is from LeetCode number 2097. We will be looking at the Haier-Holzer's algorithm for directed graph in this case. This problem is based on Eulerian path. I will explain in detail how we are doing this problem reduction and how we are relating it to the Eulerian path algorithm. And I have already made videos based on Eulerian path, Eulerian circuit, Eulerian graph and semi-Eulerian graph. This link will be present in the I button and also in the description below. You can just go and check it out. And this entire explanation is based for undirected graph, but the concepts are same. Okay. Now let's read the problem statement. In this problem, you are given a zero index 2D integer array pairs where pairs at I equals start I end I. An arrangement of pairs is valid for every index I, where I is within the range of 1 to pairs dot length, and end I minus 1 equals start I. We need to return any valid arrangement of pairs, and the note is the inputs will be generated such that there exists a valid arrangement of pair. So the answer is always guaranteed. Let's look at the constraint here. In the constraint we have a total maximum number of 10 to the power 5 pairs, and each of the pair length is 2, which is ui comma vi, right? And you can see that the start and end, that means ui vi are not the same. That means if you make a graph out of it, if it is written 2 comma 2, that means there will be a self loop on 2, right? So in this case they are mentioning there is no self loop, right? The next point is no two pairs are exactly the same. So if you have given a pair 2 comma 4, at some point you will never find 2 comma 4 again. That is not going to happen. And there exists a valid arrangement of pair, so we will always get to the result. Okay. Now let's look at an example which is already given here. You can see that we have 5 comma 1 is the first pair, then 4 comma 5, 11 comma 9 and 9 comma 4. Now in this case we want to arrange it in such a way that the end point, like if I have ui comma vi, then if vi is the end point of this pair, then the next start point should be vi, so that the previous pair and the next pair start and end value are same, right? So if you look at it, if I happen to choose this 5 comma 1, then I will always be trying to find the next point, isn't it? And the next point should have 1 as the starting point. So I will iterate for all the items and see which of the pair have starting point, and that pair should not have already been used. So I can mark all the pairs who are already used. Now there is no pair which is starting with 1. That means this must be the last pair, right? Now when I go for this 4 comma 5, if I take 4 comma 5, then if I think about what will be the next pair after it, then I will be checking what all pairs are actually starting with 5 and have not been used. So I will again iterate through this entire array and try to find out which pair is present which is starting with 5. So you see it will be 5 comma 1 itself, right? So you can place this 5 comma 1 after this 4 comma 5, and this is valid, right? So in this way, if I go for each and every element and iterate for the entire array to find out the next pair, then definitely I will be able to build the valid arrangement of pair. But in this case your total number of pairs are 10 to the power of 5, and since this is n square algorithm, that is why this will take 10 to the power of 10 operations, which is way beyond your 10 to the power 8. So this will not run within 1 second, right? So this is your brute force approach. Now let's look at an idea before looking at the optimal solution. Before looking at the idea, I'll just give you a recap about what is Euler path and Euler circuit. In Euler path, if you start from a node, you will be able to visit every edge exactly once and no edge will be left. And in Euler circuit, it is all about Euler path, but the start node and end node are same. Now let's look at an example to understand, right? So in this case, in the first graph, if you start at this 0, then can you cover all the edges at once? Yes. Without lifting my pen, I can go to all the nodes and I can cover all the edges, right? Without having to revisit an edge. An edge should exactly be traversed one time, not more than one time, okay? So in this case, an Euler path exists. But what about an Euler circuit? So the start point was 0 and where we have ended, the end point was 1. If the start and end would have been same, then this Euler path would have led to Euler circuit as well. Okay, so in this case only Euler path exists, but Euler circuit is not present. Let's look at graph number 2. In this case, if I happen to pick this 0 as my start node, then I can traverse from 0 to 1 and again back from 1 to 0. And I would have traversed all the edges exactly one time and my start and end point is same. So in this case, Euler path exists because we were able to traverse all the edges exactly one time, and we have covered all the edges. Now Euler circuit also exists because the start and end point is same. Now let's look at the third graph. In this case, if I start, let's say at 0, then I can go from 0 to 1, then from 1 to 2, from 2 to 3, 3 to 4 and 4 to 2. That means at one go, without lifting my pen, I started at certain node and I was able to cover all the edges without having to revisit an edge, right? We covered all the edges exactly once and everything got covered. All the edges got covered, right? So starting node was 0 and the ending node is 2. So that means a Euler path exists since I was able to cover all the edges exactly one time without lifting my pen starting at certain node. But the Euler circuit do not exist because the start and end nodes are not the same. If you look at graph number 4, then again if I start at, let's say, this 0, I mean if you had started at any other node, definitely you will not path an Euler path from it. So Euler path just says that you have to find a node, you have to find your own start point from where if you traverse, then you can cover all the edges exactly once and everything will get covered, right? So if you are wondering why we are always starting at 0, I will tell you in the algorithm step that we have to find our start point, okay? So now let's say that we are again starting at 0 and now I will traverse to 1, then to 2, then to 3 and then to 4. But from 4 I cannot go anywhere. So this edge here E is not getting covered if I start at 0, and you can try out from any other point as well. At least one edge will be left unexplored, right? So in that scenario, you can say that the Euler path do not exist, and definitely Euler circuit will also not exist, because what Euler circuit says is, in the Euler path, if the start and end point is same, then it becomes Euler circuit. So you can say that if an Euler circuit exists, then definitely the Euler path will exist. But if an Euler circuit do not exist, then also the Euler path can exist if the start and end points are different, but you could cover all the edges exactly once, right? So you can say Euler circuit is a subset of Euler path type graphs. Now if you look at graph number 5, let's pick this 0 to be the starting point. Now from here I can go to this 1 and come back to 0 again. Then I can go to this 2, come back to this 0 again, and then I can go to 3. So I covered all the edges exactly once, right? And our start point was 0 and our end point is 3. So that means Euler path exists, but Euler circuit do not exist because start and end points are not the same. But if I had a edge from 3 to 0 again, then I would have gone back from 3 to 0 to cover the last edge. And so the start and end point would both be 0. And in that case, Euler circuit will exist, right? So I think you have got the idea. Let's look at this graph number 6. In this case, if I start at this node 0, then from here I can go to 1, then to 2, then to 3, and then come back to 1 again. So start point was 0, end point is 1. So Euler path exists, but Euler circuit do not exist. If I had a edge from 1 to 0 again, then my start and end point would have been 0, and so Euler circuit would exist in that case. So from all these examples, you can make out what will be the start point. You know, once you are entering a node, let's say node I, then you must exit that node if that node is not a start or an end point, right? You can look at all these examples and you will understand that whenever you will enter a node, you also want to get out of that node, isn't it? Otherwise, it will either be a start point or an end point. Otherwise, the graph will not have an Euler path. So if you look at all the start points that I had taken, there the out degree and minus in degree was always equals to 1. Okay, you can check it out. Like if you look at this graph number 3, what was the out degree? Out degree was 1. How many edges are coming in? 0 edges. So out degree 1 minus in degree 0 is equals to 1 exactly, right? There should be exactly one start node to have an Euler path. Like what if I have a graph something like this, 0, 1, 2 and 3. So this 0 is pointing to 1, 0 is pointing to 2 and 3 is pointing to 2. In this case, you will find that this 0 node is actually having out degree 2 and in degree 0. So this means out degree minus in degree is greater than 1 and there should be no node like this. If there is any node which is behaving in this way, then this means that the graph will never have an Euler path altogether. In order for graph to be Euler type, you know that once you are entering a node, you should also exit the node. So the in degree and out degree of a node I should exactly be same. It should be same, right? Otherwise, how will you come in and go out? If it is a starting point, then out degree minus in degree should be exactly equals to 1. If the out degree is more than 1, then let's say this ith node has out degree 3 and in degree 1, then that means you can use this edge first and go out, and again you can come in, and if you will go out through the second edge, who will use the third edge? How will you use the third edge? You have to again come back the second time to be able to use the third edge, right? So for start node, your out degree minus in degree should be equals to 1 exactly, right? If you want an Euler path. Otherwise, if out degree and in degree are same, that is also possible, because if you have an ith node and if your out degree and in degree was same, like let's say you went out one time, you came in one time, you went out second time, you came in the second time as well. This is possible only if your graph is having Euler circuit. Like what if I take this example, graph number 2. In this case, I went from 0 to 1 and again came back from 1 to 0. So in this case, the out degree minus in degree of node 0 was 0. Okay. So in this case, it is only possible because this has an Euler circuit, right? In case you have an Euler circuit, you can take any node to be the start point. Okay. So in graph 2, you could have taken 0 or 1, any one to be the start point, and you will get the correct Euler path. Even in this graph 5, if this 3 was connected to 0, then in that case, you can start at any point, because this is having an Euler circuit. Fine. So that is the entire concept. I think you have understood what will be the start point, and with the similar reasoning, you know that for an end point, in degree minus out degree should be 1, because one extra edge has to come in so that we will stop here. In order for I to be the start point, if you come in through an edge and if you go out, then you should again come in, right? So the in degree count will always be 1 greater than the out degree count. Okay, so I hope these conditions are clear about Euler path and Euler circuit. Now let's look at a graph and try to understand the same concept of having Euler path and circuit. In any graph, if the in degree of I is even for all the node I, then that graph will have Euler path and circuit. Okay, and if the in degree of all the nodes except for the 2 nodes are all even, and the rest 2 nodes have odd in degree, that means these 2 nodes will be the start and the end points, and the other nodes are even, that means they will be just internal point on the Euler path. So you will not have an Euler circuit because there are 2 nodes which have odd degree, so there will be a start and end point, and all the rest of the points will be lying in between, right, somewhere. So this is true for one component. But if you have multi-component system, then let's say apart from this you have a 5 and you have a 6. But if you do not have an edge here, then still I can start from 0 and cover all the edges, and I can say that I have an Euler path. And that is true even if you have a multi-component system, because the definition is only for edges, not for nodes. But if you have an edge from 5 to 6, let's say, then in that scenario, it will never be an Euler path, or it will never have an Euler circuit, because you cannot put your pen on a node and start exploring one by one in such a way that you will explore all the edges. You have to lift your pen and go to the other component, isn't it? So it will not be possible. So I hope this thing is clear. So for this particular example, I can pick this as the start point, and I can go from 0 to 1, from 1 to let's say 2, from 2 again back to 1, from 1 to 4, and from 4 again back to 1, and then from 1 to 3. So my end point is 3 in this case, and this is a valid Euler path, right? If I write down the Euler path, it will be 0, 1, 2, 1, 4, 1 and 3. This is how we have done the entire traversal, isn't it? Now if this 3 was somehow connected to this 0 via another node, then my end point will change from 3 to 0. So I will append a 0 here, and so my start and end point are same. So this is a valid Euler circuit as well. This is an Euler path as well as an Euler circuit. Okay. So this is the entire concept. Now let's look at the problem's statement and try to understand how this problem is related to Euler path. Now given this problem, like a pair of items were given, right? I can imagine them as the pair of connection. Given that ui vi is a pair, I will assume that there is an edge from ui to vi. Okay, so if I am given this particular set of pairs, like 7 pairs, I can build a graph out of it by using an adjacency list, right? So if I build a graph, this is how it will look like. Okay, so from here, if I know how to find Euler path, given the graph, what I want to do, I wanted to present all the ui vi in such a way that if vi is the endpoint, then the next start point is vi, and if the next endpoint is xi, then its next a pair start point should be xi, right? And this loop should go on. So if for this particular graph, let's say that I find Euler path. In this case, I can start from 0, go to 1, then from 1 I can go to 2, from 2 to 3, 3 to 1. So you see how I have written 0, 1, 2, 3, 1, and after 1 I can go to 4, again to 5, and again back to 1. So 4, 5 and 1, right? So this is a valid Euler path. Now using this, what I can do is I can take the first pair and make a pair like 0, 1. And again I can take this 1, 2 and make another pair. Again I can take this 2, 3 and make another pair. Take 3, 1, make another pair. And this will work out for me. Because if you are taking the first pair and comparing and again taking the second pair, the first pair second item is taken as the second pair's first item. So in that way, you have the end point of the first pair common with the start point of the second pair. So given your all the pair of items, you can build a graph out of it and find the Euler path in such a way that from this Euler path you can easily form your answer pair and get the valid arrangements. So this will be the entire idea for solving this problem, and that is why this problem is based on Euler path. Now there are certain things to solve a problem with Euler path. That first thing, you have to determine that if the Euler path is even possible. But the problem statement already mentions that a valid arrangement is always possible. So I will be skipping that step of finding out if an Euler path is possible, because it will always be possible as mentioned in the problem. So let's take an example and try to apply our algorithm, which will be Haier-Holzer's algorithm used to find an Euler path for the directed graph in this case. So I'll be following 4 steps. Let's look at step number 1. Step number 1 is to parse all the edges and build an adjacency list, and along with that, while building, you also count the in degree and out degree for all the vertices. So in this case, let's say that we have 6 edges, right? So what I do is I have just given the graphical representation for easier understanding, right? But the graph is actually represented in the form of an adjacency list. I will be taking the list in the form of a map where there will be an integer to represent what is the vertex, and then I will be taking a list integer which will actually mention about what are the adjacent nodes. You can also go for stack integer or any data structure you like, or even a linked list, right? It is your choice. Now let's build the adjacency list. I will go to first a pair. There is an edge from 0 to 1. So 1 will be adjacent to 0, as you can see in the graph, right? Again 2, 1. So I'll go to this 2 and make 1 as adjacent. You can go to 4, 1. So 1 is adjacent to 4. 1, 2. Okay, fine. 1, 4. Okay, so 1, 4 is here, right? 1, 4. Then you have 1, 3. Okay, you have 1, 3, 2. So this is your adjacency list. Now while forming the adjacency list itself, I have to always update our in degree and out degree. So what does this mean? Like if I say a pair ui comma vi is present, then that means there is an edge from ui going into vi. So since the edge is getting inserted into vi, that means for vi I have to increase the in degree, because in degree counts how many edges are coming to that particular node, while for this ui I will increase the out degree. So when I was parsing and building my adjacency list, I will also increment the count of the in degree array. So what I will do is, for this 0, 1, an edge is coming out of 0, right? So the counter here will increase by 1, and an edge is coming into 1. That means for this 1 I have to increase the count by 1. Similarly I will do for 2, 1. So for 2 I will increase by 1, and for 1 it will be 2. Again for 4 comma 1, for 4 the out degree will be 1, and for 1 the in degree will be 3. Again for this 1 comma 2, so and node is coming out of 1, so this will be 1, and for this 2 it will become 1. For 1 comma 4, 2 and 1. Now for 1 comma 3, so this will be 3 and 1 comma 3, right? So 3 will be 1. Okay, so we have built the entire in degree and the out degree array along with the adjacency list. So our step 1 is done. Let's look at step 2. We need to find out the start node from where I will be actually starting to traverse. According to what I explained you earlier, the out degree at I minus in degree at I should be equals to 1 for a node to be the start node. And this is true if the graph has Eulerian path but it does not have Eulerian circuit. But if the graph has Eulerian circuit, then we will never find any node like this, and all the nodes will have in degree out degree values to be same. So we can pick any node to be the start node in that case if you have Eulerian circuit, right? In this particular example, I don't have an Eulerian circuit. If I had connected this 3 and 0, then I will have an Eulerian circuit and I can start anywhere. But I have not taken that case. So how to find the start node for step 2? I will be going through the in degree array, for all the vertices one by one simply, and I will be comparing the value of out degree minus in degree. As I had shown here, out degree at I minus in degree at I if it is equals to 1. So for this 0, 1 minus 0 is equals to 1. So initially only I found a start point. Okay. Now I will be starting at this node 0. So I know that this will be my start point. This is how you determine a start point. Fine. Let's take step number 3. This is about performing the DFS. And while performing the DFS, we have to save the node in some data structure. You can use a stack or a list. I will be going for a list. So you can save the node in path just before returning back. Just like how you do the DFS for the topological sort. Similarly, now I have cleaned up everything for easier understanding of the DFS traversal. So as you know that we will be doing traversal from node number 0. So let's start here. When you start at this node 0, then I will be seeing the adjacency list. What are the adjacent nodes, right? So in order to maintain that I do not traverse a node 2 times, I will be using the out degree. So the out degree at 0 will be telling me which index to traverse. So currently the first index has to be traversed. So if I get the exact index value, it will be 0. So I'll just decrease the the out degree value to 0, and so I will be traversing to this one. So from 0 I will be making a call to 1. So you can save a recursion call stack just to remember the current state. From 0 I went to 1, right? Now at 1, if you are using out degree for the traversal, then it will say that traverse to the third index. That means index number 2. So I'll be going to the third index, which is index number 2, and the value is 3 here. So I'll be traversing to this 3. So 3 will be pushed into the call stack, right? So at this 3, you know that the out degree at 3 is 0. This means this must be the endpoint. So I cannot traverse further from 3. So I have to backtrack from here. And if you are backtracking, I told you that before backtracking, you have to save it in your Eulerian path, and then you will backtrack. So once I backtrack, I will be reaching to this one's adjacency list, right? So I am at 1 now. Now when you reach here, the out degree value is 2. Decrement the out degree value and it will say that traverse to index number 1, which is 4. So from 1 I will be reaching to 4 and I will push 4 into the call stack, right? So I'll be going to 4. At 4 the out degree value is 1. Decrease it and it will say that we have to visit index number 0. That means I have to visit 1. So from 4 again go back to 1, right? So push this 1 into the call stack. So when you are at 1, from here the out degree is saying that you visit index number 0. So at 1 I will be traversing this 2, right? So push 2 into the call stack and then traverse this 2 again, right? Now at this 2, you see what is the out degree value here? It is saying 1. This means traverse the first index. That means index number 0. So I'll again be traversing to 1. So push 1 into the call stack. So I'm at 1 now, right? Now at this 1, what is the out degree value? The out degree value is 0. So you cannot decrement it further. That means there is nothing left to be traversed from vertex number 1. So I have to backtrack from here. So if you backtrack from 1, that has to be saved into the Eulerian path. Now you are at 2. So if you look at the out degree value of 2, it is 0. That means there is nothing left to be traversed from 2. So you have to backtrack. Before backtracking, you will save it. Now you are at 1 again. Now when you will be at 1, again the out degree value has been changed. It is 0 now, so you cannot do anything. You have to just keep on saving the values. Again the same thing will go for 4. All these values are 0, right? So you have to save this 4. Again the same goes for this one as well, and the same goes for this 0 as well, right? Because this in degree and out degree will be maintained global or passed by reference, so that any changes in the DFS call at a lower level will be affecting all the previous calls as well, right? So this what you got is an Eulerian path, but it is in reverse order. So you can just reverse it, and if you reverse it, then you will get the Eulerian path as 0, 1, 4, 1, 2, 1, 3. You can check it out. 0, 1, then from 1 you can go to 4, again come back to 1, and then you can go to 2, again come back to 1, and then finally you can go to 3, right? So this is an Eulerian path. Now in step number 4, it is saying that reverse the path to get the Eulerian path, and then you can actually have used stack in step number 3 to avoid this reversal and all. After doing this thing, you have to make the pairs. How do you make the pair? The first pair will be the first and the second item, that is 0, 1. The second pair will be 1, 4. The third pair will be 4, 1. Then you have the pair as 1, 2. Okay. Then you have the pair as 2, 1. Then the next pair will be 1, 3. And this is where you will end, right? So if the Eulerian path is of size n, then your number of pairs will be n minus 1. You can just check it out, because every time one item is in common. So this entire algorithm of finding Eulerian path is known as your Haier-Holzer's algorithm, and the time complexity of this is order of v plus e, which is linear in terms of vertices and edges, and space complexity is also v plus c due to the adjacency list, in degree and out degree arrays that we had used, right? Now in this case, the e, which is equals to the pair's length, let's consider it to be n. And if you do that, then the time complexity will be order of n, and the space complexity will also be order of n. Now, if you are solving it using unordered map, then you should remember that its lookup time and all the time complexities are actually theta of 1, which is an average O1 complexity, right? But then in the worst case scenario, it can go to linear time as well, On. So if you are using unordered map, then your complexity can range to n square, and so you might get a TLE for a very large test case. But an ordered map always performs all the lookup and every insertion deletion operation with order of log n guarantee. So if your test cases are small, then it is recommended that you follow unordered map. It will perform better. But if you get very large and worst case test cases, then in that kind of scenario, the guarantee of log n is always better, and therefore go for ordered map. So I have solved it based on ordered map, and let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this code, you can see that I have taken a set nodes, which will actually be keeping track of what all nodes are actually present. Then I have taken an ordered map. Actually, these are 3 ordered map, one for adjacency list and one for out degree and in degree maps. And then I have taken an Euler path to store the Euler path. Now this function is a simple DFS call which is used to find the Euler path. So initially I will be passing the start node here, and then it will always calculate what is the next node, and it will perform a simple DFS based on the out degree value. So the out degree will actually tell you the index, right? And we will always make the DFS call, and before returning back, I will be pushing the current node into the Euler path. So this was actually the third step, right? Now if you look at the initial steps, then step number 1 will tell you about take all the pairs and build your adjacency list and the in degree out degree array, and push all the nodes in a set so that to maintain what all nodes are actually present. Then go to all the nodes and find out if there is any node which is having an out degree value which is 1 plus in degree. That means out degree minus in degree is equals to 1. If that is the case, then that node becomes the start node and you just break out. This is step number 2. Okay, this was step number 1. Now once you break out, then maybe you did not find any node where out degree minus in degree was 1, and that is possible if you have an Euler circuit. So in that case, you make the start node as any node. You can take any node to be the start point. So I will take the first node to be the start point. After this, we will be doing step number 3, which is applying DFS to find the Euler's path. And just before returning back, I will be saving the node which I already showed you. And then in the final step, step number 4, you get the Euler's path in reverse order. So I'll be just reversing it to get it in correct order, and then build the entire valid pairs and just return it as an answer. So this is the entire algorithm. This is the Haier-Holzer's algorithm, and I hope you were able to understand it. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of this programming videos. See you guys in the next video. Thank you.